we will be analyzing a circuit, a resistive circuit, by using 10NE equations, linearly independent. So we've got a circuit here, and the number of elements in this circuit is 7, isn't it? 2, 4, 6, 7. So, and let's make it black. NE is equal to 7. So we said 2 NE equations, we are going to write. That means 14 equations. We are going to write in our analyze to this circuit. So NE is 7, okay. What about ND? ND number of nodes is 5. Let's mark them. That's 1, that's 2, that's 3, that's 4, and that's 5. The fifth one is ground, isn't it? That's the reference node. We are not going to write an equation for this because this is going to be a dependent equation. So it is totally 5. So once we've got a circuit, we know that information. From that information, we know that Kirchhoff voltage law equations, independent ones, are NE minus ND plus 1. That is 7 minus 5 plus 1 is equal to 0. Is equal to 3. So 3, that means there are 3 independent Kirchhoff voltage law equations that we're going to write. So this 3 also tells us the number of meshes in the circuit. What are these meshes? Let me draw that. So this is the first mesh. That's the second mesh. That is the third mesh. We know mesh is the one which does not include any other loop in it. This is a special loop, does not include any other loop in it. That loop is called mesh. So this 3 has got that property. So we are going to write Kirchhoff voltage law equations for these meshes. So 3 of them is going to be independent. It's going to be independent. So what about independent Kirchhoff current law equations? It's going to be ND minus 1, which is equal to, in this case, 4. Kirchhoff current law equations, independent. These are going to. And then we are going to write NE definition relations, which is 7 definition relations. Altogether, it's going to be 14 equations that we are going to write. How we are going to write it? In order to write the Kirchhoff current law and voltage law equations, we've got to do some things additionally once the circuit given to us. Look at this circuit. This circuit given to us has got some of the references already been given. What is this? For example, this independent voltage source voltages reference is given. This is practically has a meaning because the manufacturer who produced this independent source, let's say battery has got 2 terminals, and these terminals has been marked by plus and minus. So if you buy a battery, so you could see the terminals has been determined by the manufacturer. That means these references has already been chosen. Okay. How are you going to check it for the AC sources? For the DC sources, you see the battery, and then on it you can see it. How are you going to check it at home? If you use a control pencil, current control pencil, and connect it to one of the terminals in your wall plug. So one of the terminals, when you touch it, it's going to light up, So that means this terminal is the plus terminal. If you touch this control panel to the other terminal, you're not going to see any light at all. So that means this is neutral. That means that is the negative terminal. So the terminals of the independent AC sources are also given by the manufacturers or by the operating company. So in our circuit here, these are dependent and independent sources. The independent ones already given, I said. When it comes to the dependent ones, they are also given here. So that is voltage reference is given here. On the other hand, this dependent source voltage depends on a current of another element. Of this element, current reference is also given. You've got to give that reference, because otherwise the definition relation you write for this dependent source has some problems. Will have some problems. Therefore, this reference should be given. So they are all given. What is not given? All the other elements, that means elements which are not sources. These elements, references, should be chosen by you. They are not given when the circuit is given to you. So let's choose these element references. You can choose these element references as you like, no restriction on it. Why is that? Because you're going to write the equations according to these references. Meaning is this: after your calculations, you're going to find a value, voltage or current value for an element according to the reference that you have chosen for that element. So that reference tells me how I am going to connect the measurement equipment to this element in order to measure the related variable. So if you do the connection and measurement according to the reference that you have chosen for this element, then what you measure, including the sign, is going to be the one that you calculated in mathematics. So the meaning of this beginning random chosen reference tells you how you're going to connect the instrument to the measurement, this element variable, and also gives you how you're going to write mathematically the equations. So let's see it now. So we could choose the references randomly, as we just explained. Let's do it. Use this different color. So this element, current reference from left to right, this is downwards, I have chosen here. And this is make it upwards, random. Okay, and choose it from left to right here. So for these elements, we said the voltage reference has already been given. How are we going to choose the current reference? When one of the reference is given already, so you cannot choose the current reference as you like. You're going to choose it according to passive sign convention. So this current is going to be from plus to minus. For this one, make it more good one. So it's not so good. Maybe clear that. So that is the current reference for this. And for this one, current reference is going to be downwards like that. For example, when you choose, we said you're going to choose one of the references you like. You cannot choose the other reference as you like. You've got to choose the other reference according to passive sign convention. The other reference is voltage reference. Voltage reference, plus is going to be here and minus is going to be here. That voltage reference tells you how you are going to connect voltmeter in order to measure the voltage of this element. Okay, we have chosen the random references for the non-source elements. So let's write the Kirchhoff voltage law equations now. Kirchhoff voltage law equations. How we are going to write it? We are going to write it for the, we know it, for the meshes. So write it for the first mesh. Just remember what is Kirchhoff voltage law is. Kirchhoff voltage law tells us that summation of the elements voltages which belong to the same loop, algebraic summation of those elements voltages is equal to 0, it says. Assume that there are some elements in a mesh or in a loop. These element voltages algebraic sum equal to 0. Why I am saying algebraic sum means each voltage has got a sign in front of it, plus or minus. So we are going to make the decision. It is going to be either it is plus or minus while we are writing it. So how we are going to make the decision of that? That's why we have chosen the loop direction here. So if you look at this loop direction here and this current here, this element voltage, since the current reference and the loop direction is the opposite to each other, the sign in front of it is going to be minus V1. So this loop direction is the same as this 2 ohm resistor current reference direction. Therefore, it's going to be plus. Same direction, plus, opposite direction, minus. That's V2. And the third element, if you look at this third element, this element current reference and the mesh current direction is the same direction. Therefore, it's going to be plus V3. Let's give these currents numerate them. That is I1. That is, make it green one. That is I2. That is I3. That is I4. That is I5. And that is I current controlled voltage source current, isn't it? So change the color is equal to 0. So we've got 3 elements in this mesh, so that's why we wrote through in 3 terms here. For the second mesh, for this element, this mesh direction is the opposite to this element current direction, so it's going to be minus V3. This direction and this red colored IC direction is the same, so it is plus. So I made a mistake. I said V3, but I wrote VC. So that was about this, minus V3, plus, we said for this element, current reference direction and the mesh direction is the same, so plus VC. And this element current reference upwards and this direction is downwards, opposite to each other, so minus V4 equal to 0. We've got 3 elements in this mesh and we wrote 3 terms in this equation. The last one, direction of this current and the direction of this third mesh is the same, mesh direction is the same, so it's going to be plus V4, and direction of the red one and this green one is the same, then it's going to be plus once again V5, and this direction and this direction are the same, so it's going to be plus V current controlled voltage source equal to 0. So Kirchhoff voltage law equations we are writing, and these are all voltages we see here. And algebraic sum it is, some of them minus, some of them plus. We made the decision according to the mesh current direction or mesh direction. So pay some attention now. For this element, if you consider this element, its sign is positive for this mesh. That means first mesh. So here you are positive. For the other mesh, since the direction of this current and this mesh current direction is the opposite, so it's going to be negative. So it is negative here. So what happens if we choose this direction, not that way, not clockwise, but anti-clockwise? Then that means this equation is going to be multiplied with -1, so the result doesn't change, isn't it? If you multiply an equation with the same number for both sides, you get the same equation. So that means, conclusion, you can choose the mesh directions as you like. So I have chosen clockwise, you could choose it anti-clockwise. The equations you write is going to be the same equation. So we wrote Kirchhoff voltage law equations, 3 of them, and these are all independent equations because they are written for the meshes, not for the loops. For example, you could write a Kirchhoff voltage law equation for this loop, but this equation becomes dependent ones. That's why we are not writing this one, writing the mesh related Kirchhoff voltage law equations. The second step, we're going to write Kirchhoff current law equations. These are going to be independent once again, independent. So that means we are not going to write it for this reference node or ground node. We are going to write these Kirchhoff current law equations for the other nodes. We've got 4 of them. For the first one, the first node, we've got 2 currents connected. Before starting to write these equations, let's say, just remember what is Kirchhoff current law is. It says the elements connected to the same node, these elements' currents algebraic sum is equal to 0. Once again, algebraic sum. That means in front of these currents there's going to be a sign, either plus or minus. How are you going to make the decision? Easy. We are going to put a rule saying that if the current reference of an element is coming out of the node, then it is called, so the sign in front of it is going to be plus. If it is towards the node, it's going to be negative sign in front of it. If you use the opposite rule, you end up with the multiplication of the equation both sides with the same numbers, so it does not change. So you got to choose one of the rule. So the common accepted rule among the circuit theory people is the one, the current reference coming out of the node has got plus sign before it, and current reference of an element of which direction is towards the node, the sign in front of it is going to be negative. So let's do that. So for the first node, there are 2 currents, 2 elements and 2 element currents, both of them coming out of the node, so both of them has got the same plus sign in front of it. So I1 plus I2 is equal to 0. For the second node, we've got 3 elements. This IC and I3 currents has got plus because coming out of the node, and this one is towards the node, so it's going to be minus. So minus I2 plus I3 plus IC is equal to 0. So when they come to the third node, so I4 and IC coming towards the node, and I5 coming out of the node. So minus IC minus I4 minus IC minus I4 plus I5 is equal to 0. The last one, the fourth one, there are only 2 elements connected to it. So I5 is towards the node, minus I5. And ICCVS is coming out of the node, so plus ICCVS is equal to 0. These are independent current law equations. So when you write these equations, there are 4 of them. How are you going to check it? The first check is the number of elements. In this one, for the first node, there are 2 elements connected, there are 2 terms. In the second node, there are 3 elements connected, so 3 terms. And third has got 3 elements connected, so 3 terms. And the last one has got 2 elements connected to that node, and there are 2 terms in it. That's the first check. The second check, if the one element's current is positive in one equation, in the other equation this current sign should be negative. So that means opposite. Why is that? Because an element has got 2 terms. So if you choose a reference for this element, so this reference current, if coming out of this node, it must be going towards the other node. Therefore, if you are writing the equation for this node, it's going to be minus towards this node. If you are writing the equation for this node, it is coming out of the node, so the sign is going to be positive, as we see here, plus for the first equation, I2, and for the second one, minus I2. You can check the other ones as well. Why we are checking all that? Before you start to do the calculation of these unknowns. That means after we wrote this, we are going to find all the elements, current and voltages. Why we are doing this without we start the calculation? The reason is that if one of the sign is wrong, that means all your results, all the elements, current and voltages is going to be wrong, all of them. Therefore, we've got to double check before we start to do the calculation. Otherwise, the time you spent for the calculation becomes wasted. So we write 3 independent Kirchhoff voltage law equations, 4 independent Kirchhoff current law equations. What is left? Definition relations, 7 definition relations. So let's write that. For the first element, this is independent voltage source voltage. For this example, it is 20 volts. This is known, isn't it? That is the energy source. So definition relation is directly the voltage of it. So what is the current? Current, we are going to calculate it. That's the current of this element. We are going to do the calculation and learn what it is. So this voltage is independent. That's why it is called the independent voltage source. Independent from this circuit you connected it. If you connect another circuit to this voltage source, the voltage is going to be the same again. Does not change. Consider the battery that you use at home, or consider the plug that we have in our houses. So the first element. The second element is a resistor. So definition relation is V2 is equal times 2 ohm resistor is I2. That is 10 ohm resistor. V3 equal 10 times I3. And this is another resistor. VC is equal 5 IC. And this resistor V4 is 20 times I4. And this is 2 ohm resistor. V5 is equal to I5. And this one. Wait a minute now. What is the definition relation of this element is not given. So you got to find out what is the definition relation of this element. How are you going to find it out? Easy. This is a dependent source. What type of dependent source? Because of the voltage reference here, it is a dependent voltage source, of which voltage is equal to this. That means this voltage depends on another element's current. That is that element. So that means voltage source, current controlled, voltage source voltage is equal 8 times IC. That's the definition relation. So I can write it here. V current controlled voltage source is 8 times IC. Now be careful here. What about the current? So this element's definition relation is not similar to this resistor definition relation. Why is that? In here, in the definition relation of a resistor, the V3 and I3 belongs to the same element. That is, this element is named. But in here, that VCCVS, the voltage of this element, does not depend on this element current. It not depends on this current. It depends on another element current. So therefore, it is different. So you might ask that, what is this current then? This current is the one that we are going to calculate. It is not known. This current is determined by the circuit it is connected to it. So the whole circuit determines this current. So if you change the circuit, this current will change. But this relation does not change, whatever the circuit you connected it. So that's why it is different. So how many? So 7, 4, 3. So altogether we've got 14 equations, 14 unknowns. So 14 equations. Okay, we just wrote 14 equations. What are unknowns? Unknowns, currents, and voltages. So currents I1, I2, I3, IC, I4, I5, I current controlled voltage source. So this current. So altogether 7 of them. Voltages V1, V2, V3, V3, VC, V4, V5, V current controlled voltage source voltage. So 7 currents here, 7 voltages here, add them up, 14. 14 equations, 14 unknowns. So that means we wrote linear equations here. We are saying the mathematical model of a resistive circuit like that. There are thousands of infinite number of equations that you could, infinite number of circuits that you can pick up within this class. That means resistive elements included circuits. So we are saying the mathematical model for all these class resistive elements included circuits, mathematical model is the same, algebraic, linear algebraic equations. So I can show it to you now. That is the corresponding algebraic equations here. You see, that is a matrix here, and you see these unknowns, and this is known. This is known is energy source is 20 volts. So how we are transferred the equations that we write here to a matrix form? So let's examine now. So take this. This corresponds to equation. What type of equation? What it is? Just we can check it. So this is the fourth element. Fourth element is fourth unknown. 1, 2, 3, 4. That is IC is going to multiply it with this coefficient. And this. So the others, for the other variable, the coefficients are 0, isn't it? So I1, I2, I3. Why it is 0? Because it is not seen in this equation. 0 multiplied this variable gives you 0 and disappears. So if you come to here, there is another 1 here different from 0. Which variable does this 1 correspond to? Is the fourth one from underneath. 1, 2, 3, 4. That's VC. So it's going to be the VC. Yeah. So this equation here is minus 5IC plus VC is equal 0. Then VC is equal 5 times IC. That's the definition relation of the resistor of which resistance is 5 ohms. So this is this one, isn't it? So that is the one. So you can transfer this equation to that mathematically matrix form equation here. So let's check this one, for example. The first one. The first one, make it different color, maybe it is easier. The first equation here is this. So the first two terms is the first two variables here. That means I1 plus I2. All the other variables coefficients are 0. That means they are all going to be 0 equal to 0. So that is the first equations that we wrote here. So it's this one. Here on. So that means you can transfer all this a linear algebraic equation in matrix form like that. So this the first four of them here is Kirchhoff current law equations, and this three here, Kirchhoff voltage law equations, and the rest of it here, definition relation. So if you represent this matrix equations, it becomes A, that's the square matrix, multiplied with X is equal to B. What is inside in B? That's independent source. It is known, isn't it? Known column matrix correspond independent sources values here, isn't it? It is included the independent source here. So everything depends, all these current and voltages depends on that energy source. Energy source changes, these element current and values, current and voltages will change. This is unknown matrix, unknown column matrix. That is this. So 14 of them. And this is the coefficient matrix. This is a square matrix. Since we wrote these equations which are independent from each other, independent equations, then the determinant of this A matrix is different from 0. That means you can get the inverse of it. That means you can calculate this one. So that means X is minus A1, B gives you that. You can see many conclusions from this. Here B is the independent source. So that means all the elements, current and voltages depends on that source value. When you change the source, they will change. What else these elements, current and voltages depend on is this coefficient, the A matrix elements. A matrix elements here is plus, minus, and 0, 1 comes from this Kirchhoff current law and voltage law equations, and nothing new. But what else we've got here is there you see some parameters here. These parameters are the definition relation parameters. That means that coefficient that you see in the definition relation of these elements. So this is seen here. When you get the inverse of this A, these coefficients are going to be transferred to here. So your element current and voltages depends on sources plus the element parameters. So that is the mathematical conclusion that we can get out of this. So that's the end of this video.